Hello and welcome. This is Chapter 8, Section 4, and it's a more general section called Reasoning about Circular Motion, and it's really the book's attempt to talk about non-inertial reference frames, and also sometimes we call them centrifugal forces, sometimes more generally we call them inertial forces, but this book is a nice introduction to inertial forces. First of all, we look at this picture of the car making a left turn. So from our inertial standpoint, like a bird's eye view, like we're a bird on the lamppost of the street watching this car turn, certainly we see that the car is, turning it would be counterclockwise, and since it's moving in this circle, we observe that it has an acceleration towards the center of the circle. That's the inertial frame reference. But you've obviously, if you've been in a car and turned, made this turn, you'll see that you're feeling a pull outwards, or you're still feeling some sort of pull, whether it's a pull or a push, you're not sure, but this object diagram says you're accelerating towards the driver's side door, and yet what you'll feel is being pulled or pushed somehow towards the passenger side door, all the while you're moving forward, say in the direction of the windshield. And so this really gets at the differences between our direction of motion, our acceleration, and what we happen to feel if we're the ones accelerating. A couple other examples before jumping into the next few slides are even just moving in a straight line. If you're speeding up or slowing down in a car on a straight road, when you brake, like so you're driving towards a street light, it turns red, you brake, come to stop, you feel flung forward, and yet you're accelerating backwards. And then once the light turns green, you accelerate forward, and yet you feel flung backwards. And so we sometimes call these, the circular one, we call it centrifugal force, and it's easy not to get too confused as to what it is, because there's really nothing pushing you outward towards the passenger side in this figure. In fact, it is your inertia. All these chapters 5 through 8 really hinge on this conception of differentiating between inertia and force, and certainly this is no different. And for the slowing down or speeding up case, when you're driving, say, on the road in a straight line, your sensation of feeling flung forward as you brake it doesn't have really a name. It's just called an inertial force. Sometimes books call it an inertial force, which can be confusing, but it's really the result of us being what's called a non-inertial reference frame. Non-inertial reference frames, of course, are systems, coordinate systems, with meter sticks and stopwatches that are accelerating with respect to what we call an inertial reference frame that you learned in Chapter 4. Inertial reference frame is one that's moving, where the coordinates is moving at a constant velocity relative to another, perhaps one at rest, or another one moving at a constant velocity. So these are all effects of these non-inertial reference frames give us these fictitious forces. That's really what they're called in general, fictitious forces. And certainly it's not any different on the surface of the earth. If you think about, let's say you're on a merry-go-round, you're on a spinning merry-go-round, you feel flung outwards away from the merry-go-round, right? If you, weren't planted firmly on the surface, or if you weren't grabbing onto, the sides or something, you'd feel flung outward, and you would fly off in a direction tangent to your motion at that time. And it turns out that you're feeling the same effect while being on a rotating Earth. Why can't you feel it? Why don't we feel pull outward? Well, Earth's gravitational pull is so large. So if we look at a point on the equator, so we have on this figure here an object on the equator, and then this is like a scale. Is that right? Yeah, we have a spring scale or some device to measure like a normal force. Okay. What we'll observe is that our gravitational force on the equator the force of big M, the mass of the planet, on the mass of the little object M is the mass times actually more like 9.83 meters per second squared. So on the equator, well, anyone on the surface of the Earth, if you assume the Earth is a sphere, which it's kind of like a sphere, it's more closer to a kind of ellipsoidal because it kind of bulges outward, actually precisely from this reason. The gravitational force is technically mass times 9.83 meters per second squared. Why don't we use 9.83 meters per second squared in all our problems on free fall and projectile motion and in boxes sliding down inclines? Well, because of this rotation effect. And it turns out that the net force, because the net force on an object on the equator, all right, we feel this sort of inertial pull. So we have to have an acceleration inward, a centripetal acceleration inward that's equal to the rate of rotation of the Earth squared times the radius of the Earth. That's slight canceled with the gravity. And so what we measure as normal force ends up being M times 9.80. This effect decreases the further higher you go in latitude. For instance, people on the North and the South Pole, they don't feel this rotation. Someone standing on literally on the top of the North Pole, their mass, or sorry, their gravitational force would literally be mass times 9.83 meters per second squared. And if you think about 0.03, it's about maybe a half of a percent or 0.3% off of the weight. And so there have been experiments that are done where you take a person, stands on a spring scale somewhere in the North Pole versus someone in the equator, and their difference in weight is like, 100 and maybe 195 pounds on the equator, 200 pounds on the North Pole or South Pole because of this rotation effect. So this is another instance of a rotating system giving us a fictitious force that gives us a smaller sensation of gravity. Another interesting topic about circular motion is making sure we understand the loop-the-loop. It's the classic roller coaster problem where you take the turn fast enough to where when you go inside that circle, you manage to go fly inside of it, and you can still make it over. Well, as these slides say, this is certainly not uniform circular motion, right? Because you go in with a certain large speed at the bottom, your speed is going to decrease and have a minimum speed at the very top of the loop, and then increase, ignoring friction back to its original launch speed. And so the force analysis of this can be pretty tricky, so it's worth discussing how these forces add together. You got to be careful with the minus signs in particular. And so this next slide goes into what's going on at the bottom. Right, it's the roller coaster free body diagram at the bottom. So if we look here, we see what are the two forces? Well, there's obviously gravity pulling down, F sub g, and you see that's a very little thing. But since we're moving in a circle, even at the bottom where it feels like we're on a flat surface, starting to go up the circle, we are moving in a circle, and so we have to have an upward acceleration, which means we have to have an upward net force by Newton's second law. And so to resolve that, we need to have a much larger normal force than the gravitational force. From the discussion of chapter 6 on mass, weight, and gravity, that means you really feel shoved down into your seat when you're on the roller coaster at this spot. The last time you've been on a roller coaster, once you're at the very top, when you go down and then just start zooming back upwards, you just feel like shoved down into your seat. And that's what's going on with this normal force, is that you have an extremely large normal force because you have inertia. You want to keep going straight. And so the seat in the roller coaster has to say, no, I'm going to push you upward to keep you moving in that circle. And so in looking at these equations, we've got MA, right, the net force, has to equal plus normal force minus mg equals plus MA, or plus velocity at the bottom squared times or divided by r. Right, and if you continue that further, what's going to happen? There's no limit to how the faster you take this bottom, the larger the normal force is going to be. And there's really no limit to how fast or how slow you can take the bottom of the circle. The normal force will just get smaller and smaller until, if you imagine the roller coaster sitting at the bottom of the circle at rest, n equals mg, and there's 0 F net. That is quite different from compared with the top of the slide, or sorry, the top of the loop-the-loop. So considering the top, now there is a new issue that comes up, because gravity's still pulling us downward, but since we're at the top of the inside of this circle, we're in contact with the surface at the inside of the top, so normal force actually points down. And if you use the correct coordinate system, in the RTZ coordinate system, we have R pointing down towards the center of the circle. T, I guess T would point to the left, and then Z points, in or out somewhere at the screen. The equation would be plus normal force plus mg. This is a rare instance where the normal force adds with gravity to give us our net force, which for circular motion is still mv squared over r. Now, it might not seem like a big deal, the difference in those signs between top and bottom, yet there is a minimum speed with which you are allowed to navigate the top of this loop-the-loop. There's no maximum speed, of course. The faster you take the top of this curve, the larger the normal force is going to be, right? Because gravity's fixed. Gravity's not going to change. As far as we know, gravity does not ever depend on how fast you're moving, or if you're accelerating or not, or slight dependence on position, but these small enough distances, negligible. So normal force would increase the faster you're taking the top of this curve. But the slower you take the curve, the smaller the normal force would be. But eventually it'll get to the point where the speed at the top is so small that the net force, which has to be pointing down, approaches the magnitude of the gravitational force, which would make the normal force 0. So at that certain speed, we call it the critical speed, because at that speed, you can barely take the turn. You're actually momentarily weightless. The surface is not, you're barely in contact with the surface, the seat of the coaster, and you have normal force is 0. And at that point, when looking at that equation here, if normal force is 0, then that's going to make masses cancel. That's going to give us an expression for what we call the critical velocity, being square root of RG. Yeah, square root of RG shows up many times in chapter 8 in different forms, being radius and free fall. So that is what's happening at the top of the loop-the-loop. Okay, and sure enough, we have this result right here that I was mentioning, that the faster you take, the slower you take the top of this curve, the smaller the normal force is, and the normal force will never flip directions to allow for a smaller net force than gravity. As some physics instructors like to say, surfaces don't have hooks. And of course, for a realistic roller coaster, I mean, this is like kind of like a Hot Wheels track where it's just the track and the car. But rear roller coasters obviously have tons of safety mechanisms in place. You're not going to, even at the top there, you're still firmly in your seat, and the roller coaster is firmly attached to the inside of the track. I mean, there's designed the safety. And then finally, here's kind of a picture of just what happens at different stages. The faster, or if you take it at less than the critical speed. So if you here at the bottom here, if you're taking it at less than the critical speed, now your trajectory becomes a parabola. your trajectories of parabola, you don't quite make it because you have a smaller speed than the critical speed. Another thing that the slides don't mention that is just worth a minute to talk about would be the kind of the opposite effect of the loop-the-loop, and that's going over a hill, kind of the speed bump problem, or sometimes we call it like the problem where you're trying to sail a car over a hill. Really quickly, just because I think it's completeness. So what's going on at the top of the hill? Well, instead of having a minimum velocity with which you can take the inside, there's actually a maximum velocity with which you can take the top of this hill and still make it safely over on the circle. Okay, I'm drawing on the PowerPoint slides. And so in this instance, what does the free body diagram look like? I'll draw it above it. R still points down, and we still have F net pointing down because we're at the top of the circle, but we're still moving at the top downward in the circle. So F net has to be downward. Well, you have gravity downward. Now normal force points up again, and it's always less than or equal to mg. It's always less than or equal to mg because, right, if it's at rest, then F net would be 0 and n would equal mg. But in order for there to be any motion at the top of this hill, there has to be a small net force downward, which is by Newton's, just by the definition of F net, that's going to necessarily force n to be less than mg. And so this will continue up until you reach the speed at which n becomes 0. Once again, n doesn't flip. The situation just changes. So if you take it too quickly, and in fact, if you sum the forces, now you get n minus mg equals the same mv squared, mv squared over r. Actually, there's a minus sign. Give myself some more space. It'd be plus n, and no, actually it would be minus n, because we got to make sure our coordinate system is correct. It's minus n plus mg equals plus mv squared over r, because the r is positive downward, and that's the r coordinate, and this is the r radius. So once again, when that normal force goes to 0, you get the same v equals square root rg expression for the critical velocity, but it switches roles. It's now the maximum velocity you can take the hill without flying over. And then you become a parabola that's bigger than the circle. So reason about vertical circular motion can get kind of confusing, to say the least, but these are two simple examples that are worth going through and understanding. So that's it for this video. In the next video, we will conclude chapter 8 with a discussion on non-uniform circular motion. Until then, thanks for your time. Take care.